Okay, so the notes that we are going to take today are called the physics of sound and the Doppler effect. And so at this point in time, everybody should have the physics of sound note handout. So if not, if we could take a second to pause the video and distribute that. Now, these notes that we're going to take today, I am going to cut these in half. So we're going to do half of the page today and then the other half of the page tomorrow. And then I do also have a couple videos that I'll be playing too. So we'll pause, the notes and play those videos when we get to it. But the first portion of these notes is going to look at sound. So what makes a sound wave different from other types of waves, like a man-made wave or a light wave, an electromagnetic wave. And then also look at properties of sound. So what are some things that we could alter about the sound wave to change the way in which we hear and perceive the sound? Sound itself, by definition, is pressure variations. So pressure variations or pressure differences caused by vibrations transmitted through matter. Pressure variations caused by vibrations transmitted through matter. So kind of a long, fancy description that's, in short, describing it a little bit easier. So pressure variations, so differences in pressure formed when something vibrates, something shakes, something moves, and it's transmitted, it's going to travel through matter. So sound does need a physical medium, something physical to move through. Sound is a longitudinal or compression wave, another word for that. So the longitudinal waves, that's when something vibrates and the wave moves parallel or in the same direction as the vibration, versus a transverse wave where it's perpendicular. Now, how sound is generated, how sound travels, is kind of simple here. So as an object vibrates, as an object shakes, as it moves. So for example, this speaker here, as that speaker is vibrating, playing music, I'm sure at some point in your life you've listened to music very loudly and you could see or at least feel that speaker shaking. As that speaker shakes and moves, it's going to actually bump and shake the air next to it. Even though we can't see it, air is a form of matter. There is something physical there making up air. And so when it vibrates, these air particles are going to get compacted. They're going to get kind of squashed together. And since they are moving themselves after that compaction, they're then going to push and bump into the air particles next to it. And the process is going to continue with compression, push, compression, push, compression, push. And so it's going to be repetitive. It's going to repeat itself until it eventually reaches your ears and you perceive that as sound. Now, the term resonance can describe kind of how something creates a sound, how a sound is made by vibrating something, so by vibrating matter. So resonance is described as when the frequency of a force applied to a system matches the natural frequency of vibration of the system. We'll give everyone a second to write that down, and we'll talk about kind of what this all means. So when the frequency of a force applied to a system matches the natural frequency of vibration of the system. So what resonance kind of means, and we'll talk about, and I'm going to kind of jump into pitch here shortly and talk about how these two things kind of go together. But every type of object material, so it is made of some sort of physical form of matter. And so depending on what it's made of, that object has a natural frequency in which it can vibrate. So if you apply a force strong enough to it, it'll make the object shake, it'll make the object vibrate. And so if you apply a force at a frequency that matches that natural frequency of vibration, that will cause that object to vibrate, and that will then emit sound. Resonance is a phenomenon used in music, playing musical instruments. All of our different musical instruments, whether it be a guitar string or whether it be blowing into a flute. So those are all made of materials that can be set into vibration at a particular frequency. So you can set that material into vibration, that guitar string or that instrument that you're blowing into, like a flute, by applying a force. So that force could be the pluck, that force could be blowing air into it. And so if you blow air into it at the right frequency, or you pluck a string at the right frequency, that'll cause that material to shake, to vibrate, and to emit a sound. Now, how we perceive that sound is in the form of the pitch of the sound. And so pitch is a way to describe the frequency of vibrations. So frequency of vibrations. So depending on how much the vibration is, the higher the frequency, so the more wavelengths occurring in a period of time, the higher the pitch is going to be. So in music, when you're playing a musical instrument, the different frequencies of sound waves that you create, these are the different notes that you are playing. And so in general, the higher the frequency of the wave, so the more energy that wave has, the higher the pitch. So higher the frequency, higher the pitch. So our first video that we're going to watch is going to give you a bit of a visual of kind of all of these things, but in action. It's pretty short. We're not going to watch the whole thing, but what we're going to watch here is going to be a couple individuals that are going to play a song here for you using water glasses. And so the water glasses, you'll notice, are different sizes. And the different sizes of water glasses, along with different amounts of water to create different air columns within the glasses, you should be able to hear different pitches that are going to be played. Give me 1 second just to switch gears here. And so while you're watching the video, you'll notice that the glasses on the left are going to be much smaller in size. And you'll notice that as they're playing, you should be hearing a higher pitched sound coming from the woman that's going to be playing the smaller glasses. And then the man on the right playing the glasses that are taller, that are bigger, you're going to hear a deeper, lower pitched sound. So that's all going to be based on the resonance of the glasses, the different sizes, the different amounts of water filled in them is going to create different pitches because they're going to be vibrating at slightly different frequencies, thus altering and creating slightly different pitches and notes for you to hear.
It's a recording. Not a playback. It's not playback. Just recording. Okay? It's true.
Okay, so moving back to our notes here. Let's see, just got to fix I lost my camera, so let's get that fixed here. Oh, sorry about that technology. Here we go. Try and reboot it. There it goes. Okay. So pitch, that is one thing that we can alter, one sound property that we can alter. Loudness is another thing, so how loud or soft the sound is. So the loudness of a sound, how loud a sound will be perceived, that depends on the amplitude of the sound. Or the amplitude of the compression wave. Now, this way in which we visualize or measure amplitude when it comes to compression waves is the differences in pressure variations. Differences in pressure variations. So it depends on the amplitude of the compression wave or the differences in pressure variations. Now, sound is a longitudinal wave, so it does make it a little bit more difficult to visualize difference in amplitude than in a transverse wave. And generally, too, transverse wave properties and how they look is often used to measure to give you a visual of what's happening with the sound wave. So a louder sound is going to be one that has a higher amplitude. So on a transverse wave, when we're looking at a transverse wave here, higher amplitude means that we have a higher displacement from the mean position. So It's a taller wave than one that has a lower amplitude. So in sound waves, compression waves, higher amplitude is visually going to look like stronger areas of compression or greater differences in pressure. If I compare these two pictures here, the areas of compaction of the air particles are tighter together. So here, these little dots representing air, they're tighter, closer together than down here. And then I have a area of space without air, and then air that's compacted together. So tighter areas of compaction of the air particles means a louder sound. There's a more violent force, a more violent vibration that's compacting these air particles at a much stronger rate than one that is lower, where the air particles are more spaced apart and not as tight, a lot less compact. So loudness depends on the amplitude. The greater the differences in pressure or higher displacements of the wave, if we're using a transverse wave visual, whereas pitch is related to frequency. So the more waves occurring in a short amount of time, higher frequency is going to give you a higher pitch. Okay, so flipping our paper here. So focusing on those pressure differences, I'm going to put a little note there, even though I kind of already mentioned it. So the greater the difference in pressure, so the greater the difference in pressure, the greater the intensity of the sound wave. And you throw in there and energy. So higher energy means it's more intense, means it has a greater difference in those pressure variations. Now you might see here and there a unit called the decibel. We're not going to really do a whole lot in decibels, but you'll probably see that unit here and there, though, as a measurement. So this measurement of sound intensity, so again, kind of how loud, how energetic that sound wave is going to be, can be measured using the decibel unit. It is logarithmic, so it goes by like bases of 10. And to give you an idea of kind of what the scale looks like when you see a number, 10 decibels is barely audible, so like a soft whisper. Whereas 110, that's when it's going to start to get to be painful to your ears. While you're standing next to the woofer at a really loud concert. So in this little diagram here, just kind of a summary between the two properties with sound. So quieter sound, smaller amplitude, louder sound, higher amplitude. Pitch is related to frequency. So deeper, lower pitch when the wave is less frequent. Higher frequency wave is going to have a higher pitch. So this last little section of our notes, we're going to look at a phenomenon that's related to sound and pitch known as the Doppler effect. And this is where I have another movie that we're going to watch at the end of this note, the end of these notes. And what the Doppler effect is, by definition, is the apparent change in pitch of an object, or it could be, I guess, a person, just anything that's emitting sound. The apparent change in pitch of an object. As the sound source. Or observer moves. So the apparent change in pitch of an object as the sound source, so being the object, whatever is emitting the sound, or the observer being someone that hears the sound, observes the sound as they move. And remember, since we're going to talk about changes in pitch depends on the frequency of the sound wave. So pitch depends on the frequency of the sound. So now what the Doppler effect is it's an apparent change in pitch. So we have a sound source, something that is emitting sound, and if that object, that sound source, is stationary, so it's not moving, it's going to emit those sound waves evenly in all directions. So that sound is going to sound like the same pitch no matter where your position is around the source that is emitting a sound wave. So where the Doppler effect happens is when something is emitting sound, but it is moving. And so based on your position, sorry, we'll let that bell go. So based on your position to the sound source, those sound waves are going to sound higher or lower pitch or at a higher or lower frequency than what they actually are, simply because that sound source is moving. And so probably the most common example you've ever experienced with the Doppler effect would be if you were hanging around outside and either an airplane goes over your head really quickly, or you are outside or in your car and an ambulance siren goes by or a police siren goes by. So as a sound source starts to move towards you, as the sound source moves towards you, what's going to happen is the waves get crowded in space. Not obviously outer space, but just the space around you. So as the sound source moves towards you, the waves are going to become crowded in at space. So the siren here is emitting sound waves in both directions, but because it's moving forward, this police siren here, it's going to compact those sound waves into a smaller area of space. And so as that wavelength is shortened, that's going to increase the frequency of the sound wave. So you have more waves occurring in a smaller area of space, and that's going to create a higher pitch. Now on the opposite side, if you instead are not facing the direction of the sound source, so you're in the opposite direction, those waves are going to get stretched out, get elongated. And so as you move away, the wavelength is lengthened. and the frequency decreases. And so as a result, the pitch is going to decrease, or it's going to be lower. Now, sound-wise, so what you might hear is that plane zooms over your head, or as that siren whips on by you, is something like this. We'll have a better description later, or a better example here shortly with our video here. But you've probably heard it be really, really loud as it comes towards you, and then drops a little bit lower as it goes past. So coming towards you, it's that higher pitch, that knee, and then as it's going past you, you hear that little drop. Yeah. Now, this can also occur. Well, we generally describe the Doppler effect with the observer, the people stationary, and the sound source moving. This can also occur if the sound source is stationary, but the observer moves. So it can also occur if the sound source is stationary, but the observer is the one that's going to end up moving. All right, so we have one more quick video that we're going to watch, and then that'll be it for the notes today. So this will give you a better visual, more live action idea of what's happening with these sound waves. And then a bit of a more accurate example of how the Doppler effect sounds instead of my not so great noises that I'm making here for you. And then after that video, we'll be all set with our notes for the day. So let me just get that video pulled up, and we can get moving on to our next thing on our agenda.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light.
All right, so that is going to be it for our video for the day. So we're going to move on then to the next item on our agenda. Hope you're all doing well, and have a good day.